Welcome everyone to our Support Vectors weekly paper reading. Today's topic is quite interesting. It's a survey paper, sort of. The topic is LLM post-training, a deep dive into reasoning large language models. Now, clearly, especially since the arrival of DeepSeek R1, we are in the age of reasoning models. Reasoning models started a little while ago with O1, and even before that, reasoning models have been making their way in. So this paper is a survey. It's a fairly recent survey, about a month old, and it covers a lot of the reasoning models. The models that you can see in figure 1 are on the outer periphery of it. There are lots and lots of models being mentioned here, and we'll talk about it. Now, the word reasoning model is interesting. Ever since the LLMs came about, people have said that they have some capacity to reason. Ever since GPT 3.5 itself, the first instruct GPT, or what was called instruct GPT trained model, I'll just put the word there, just a bit of the history. So a little bit of the history. We started with the paper instruct GPT, where there was a process mentioned to train what today we call large language models. And essentially what it meant is you would take a transformer, especially a decoder part of the transformer, a GPT based or decoder based transformer, and you would pre-train it with the world data. People often call it unsupervised pre-training. The word unsupervised is a bit of a misnomer. What you do is quite often play games, like, for example, you say the cow jumped over the what, and then you attach a negative log likelihood to the probability of the word moon, because you expect the word moon here. Right? So you can train it like that. So theoretically, it is actually a supervised learning, but you do it simply by manufacturing a supervised row of data from the general web text. And so colloquially, we always call it unsupervised pre-training of these very, very large language models. After this was done, and this is just to recap the history of LLMs in a very brief way, the problem is if you ask it, what's the capital of California? It is equally likely to say, what's the capital of Colorado, instead of saying Sacramento or something like that. And the reason for that is in the pre-training data, the world data, you're as likely, so I'm just obviously caricaturing it a little bit, as likely to have just a list of questions as you are to find a question answer pairs. Right? So for example, for every document that gives you what's the capital of California, and the answer is Sacramento, there might be another quiz list, which is what's the capital of California, what's the capital of Colorado, and so on and so forth. So the machine, without further instruction, could go either way. That's, of course, oversimplifying it, but that's the main problem with pre-training. It is not sort of aligned with the sort of answers we expect. And so we need to go through further training of this model, which was the whole process that Instruct GPT mentioned. A part of it is supervised fine-tuning. You can take label data. For example, you can actually give it an example. You can say, what's the capital of California? And the answer should be Sacramento rather than another question. And then you put a loss function on top of that fine-tuning. So you can feed it to a fine-tuning. This would be a genuine supervised fine-tuning with label data. Now, when you do supervised fine-tuning, a host of issues come up. First is creating label data is extraordinarily expensive. The web is a vast scale data. You can, these days, we talk in terms of 1 trillion, 2 trillion, many trillion data sets, token data sets. All those tokens are available for you. On the other hand, no one in his right mind would set out or embark on creating even a billion, I would imagine, a billion rows of supervised fine-tuning data or a trillion rows of supervised fine-tuning data. That would be practically infeasible. It would be prohibitively expensive. So given the fact that the label data, the fine-tuning data size, the size of the size is necessarily modest compared to the size of the model, that leaves the potential open for model doing overfitting, right? So it leaves the potential open for overfitting. And at the end of the day, if you notice, if you put just a loss function on just a negative log likelihood, so suppose you say the log of the probability of the correct answer, probability of the label produced by it, or rather negative, which is the same as negative log y hat for the label, right? What is the predicted probability for your label? In that particular case, you are making two problems arise. One is that of overfitting. The second is these are necessarily next token loss functions, right? Aggregated over next token, next token, next token, which was one reason people always felt that these LLMs were next token prediction engines. Now, things have improved a little bit over the years, but with that being what it is, let's go back and see. So the next point was, even when you did that, you took care of this, there was still alignment to human values. How do you align it to not be toxic? Because this data that it was trained on is pretty toxic. The pre-training data is quite toxic, biased, and misinformation, quite often conspiracy theories, etc., etc. It's a pretty toxic pile of data. Internet isn't a very trustworthy place in general. So when you pre-train, you're essentially producing a sort of an intelligent monster, and that intelligent monster needs to be tamed. And supervised fine-tuning is a step in the right direction. Nevertheless, it is not a complete alignment with human values. And so the next thing you do is you bring in learning, reinforcement learning with human feedback, right? RLHF. And then the model that comes out of it is the model that you call an instruct GPT, and people often call it instruct train model or instructed model and so forth. There are lots and lots of words that people have used in this space for this sort of model. So this is the history of the field. Now, what is the problem with RLHF? With RLHF, there are two fundamental problems. First is RL is hard. It's much harder than supervised fine-tuning. It has historically always been a harder problem to solve. The second thing is RLHF is not really true reinforcement learning. And that statement needs a little bit of a elaboration. So in the Instruct GPT, the idea was this, that if you take a model, an LLM, let's say that it has to go through RLHF, what you would do is you would give it a query QI. Let me just write it as Q, and it would produce multiple outputs. It would produce output 1, output 2, output 3, output 4. And why is it doing it? Because we are sampling off the last layer, because we are using a sampling of the softmax. So sampling off just means that to find the next token, you necessarily don't take the most likely token, the high probability token, but you take from one of the high probability tokens. And so that is called nucleus sampling, which is very common, of the softmax. And so if you sample off it, it introduces stochastics into it. It becomes a stochastic machine at that. It means you lose determinacy. You give the same query, next time you'll get a different answer because you're sampling off. It's a randomized process. And so you can get many, many responses out of that, k responses of the output that you can get, output you can get. Then what you do is you give it to humans to stack rank it, the responses on which is better. And now comes a problem. Human beings are very bad actually at stack ranking. So what you do in practice is you give a human being two of the responses and ask which is better. Then you give another two and ask which is better. And you do it across a lot of people. And what comes out at the end of it is effectively a stack ranking of the responses. Now what do? You have a query QI, and you have associated with it a stack ranking of responses. Best response, a little less better response, good response to worst response, right? You have a stack ranking of the responses. What you do is you train as what is called a reward model. And that brings us to the constructs of reinforcement learning. You train a reward model such that it learns to, for each of these outputs, learns to give a reward in such a way that the stack ranking would be preserved. So it would give more reward for the best answer, less reward for the better answer, etc., etc. So in other words, reward model becomes a neural network in its own right, a neural net whose job is to, whenever you're given these outputs, it should be able to give rewards that preserves the ranking order in effect. So that's a reward model. And then what you do is you apply the rest of the machinery of of reinforcement learning. You bring in something called a policy optimization. And the first policy optimization used in the paper, Instruct GPT, I believe, was PPO, proximal policy optimization. So we're going to talk about all of these concepts because a little while ago, some people told me that actually this paper would be far easier to understand if they had some background at least with reinforcement learning. So I would like to. So now, while all of these things we do, at the end of it, you still end up with an LLM in which a query goes out and a response comes out. Response to the query comes out. Now, the question is, while you have aligned this response to human values and human expectations, and because the LLM has learned from the world knowledge, it has become considerably useful. It is producing the right answers most of the time. It nevertheless has a whole slew of problems. It hallucinates. Well, that's a perennial problem with the LLM. But more particularly, it seems to be not capable of long chain reasoning. So people notice that you couldn't give it a math problem and it would solve it. So that led to a whole flurry of activities and what people often call test time compute and so on and so forth. What people did is they started putting, to prevent hallucination, of course, they started putting a retrieval system next to it. So it became a RAG system, retrieval augmented generation. These are things that we are all familiar with, I hope. Or they would start adding chain of thought and tree of thought and graph of thought and whatnot, processes to it. They would start doing all sorts of Monte Carlo search, tree search, etc., for optimal answers. They would do all sorts of things to take that trained model and at inference time get good responses from. And most of us are familiar with the whole spawned subfield, which is called prompt engineering, right? And prompt optimization and so on and so forth, and retrieval augmented generation. These have become very, very popular topics. Now, that is the general history of this. But the one sort of a missing thing was, in all of this, we didn't know how to train the machine to reason at train time, not with not at inference time, but people call it post-training. If you notice that LLM post-training, what they meant is post what? After what? Post, of course, stands for after. After what? After the pre-training. After you have taken a model and pre-trained it with the web knowledge, you end up with a pre-trained monster. You have here you have a pre-trained monster. Everything that you do after that is called post-training, which would include supervised fine-tuning. It would include reinforcement learning with human feedback. It would include pure reinforcement learning. And it would also include test time methods like RAG and so on and so forth. You know, all of your prompt techniques, tree of thought, chain of thought, etc., etc. To all of it geared towards eliciting better and better answers from the large language model. So this paper is about that. But this paper leans quite a bit into reinforcement learning for a reason. Inducing reasoning just by giving it examples as chain of thought. Let's say that you take a chain of thought. Chain of thought was, Mary had, like you basically show the steps with a few examples, with a few short examples. You would show the chain of thoughts, A step, B step, C step, D step, and then you ask the machine to reason like this and to once it starts reasoning like this, to be able to hopefully solve mathsy problems. The discovery of chain of thought was, of course, quite a remarkable discovery. Nevertheless, its effectiveness was poor in the sense that these machines couldn't do very complicated reasoning. At the end of the day, you couldn't do that. So people tried to do supervised fine-tuning on chain of thought itself. And or they said, can we do other things? I mean, there are many, many efforts that went into it. But let's fast forward to today. Today, if we live, ever since DeepSeek came out, the world has been turned upside down. Our world, R1 came out. This has been a wonderful sort of a seminal movement. It led to a lot of simplification. It led to a lot of changes. One of the things that we can say, at least from the open source perspective, is we finally had a model that in which reasoning was an emergent, almost an emergent phenomenon. You would train the model through pure reinforcement learning using a process called GRPO. And again, these are terms that I will explain as we go along. Using GRPO, a group relative policy optimization. And what you would notice is, as you did that and you let the machine reason for longer and longer time, or you gave it more complex problems, it would actually start reasoning about it. Right? So quite a remarkable discovery. And if you read the paper, you can literally see the excitement of the researchers is very poorly concealed when they say, wow, can reasoning be an emergent phenomenon in a way? And it seems to emerge just through pure reinforcement learning. Right? And so that is why today, when we talk of reasoning models, invariably we think of, amongst other things, one of the core things we think of is reinforcement learning. Right? It has become front and central in how we train these models. It doesn't mean that that is necessarily the only way to bring about reasoning in models. An alternate approach is to take just supervised fine-tuning, but with a lot of chain of thought samples, and bring really good examples of chain of thought and do that. And that was another paper which was from Stanford. I believe it was called S1 and something. We covered that. So there are various approaches, but we are going to, well, this paper is all about that. So let's read this paper within that context. Now, okay, so one more thing. So what exactly is reinforcement learning? I'll give a very abbreviated and simplified understanding of reinforcement learning. So it makes it easy for us learning. What it is think the way reinforcement learning thinks of the world is a piece of intelligence that is usually called agent. Agent is basically your LLM, right? It's a reasoning agent. It's capable of thinking, let's say. Colloquially, you can say it is capable of thinking. More specifically, just think LLM, right? LLM engages with an environment. So the agent engages with an environment. It gets signal through observe, and it acts upon the environment with an action. And the idea is internally, it will somehow reason or think about it, about the observation. So the environment will be in a state S, right? The action will be A. So let's say that AI is the action, state I, and observation is just seeing what state the machine is in. Environment is in. And so in the language of reinforcement, the thinking is quite simple. Imagine that one easy way to think about it is, people often give the example of Roomba or autonomous vacuum cleaner in your room. When you first put it in a room, the room might be pretty dirty. So the state is a dirty carpet. And there's some furnitures here and there. And as the Roomba acts, the action of the Roomba or of the vacuum cleaner could be take one step forward in some direction and vacuum the bit of carpet underneath. Right? And that may or may not be productive. It may or may not lead to a result that you want. For example, if that you don't want it to keep on, the next action being keep on vacuuming a place it has vacuumed. Right? So associated with every action, there has to be a reward. Action, a reward, right? A reward that tells how good that action was. But how does the machine figure out what action to take? Because it might have access to it many actions. For example, if you put a little autonomous vacuum cleaner in the middle of the room, a Roomba in the middle of the room, it could go in any one of those directions, 360 degrees. And some directions are better pursued, some are not. For example, if it moves against a wall, it will hit a wall. It might get a negative reward. Right? It has hit a roadblock and it needs to change directions now. If it, on the other hand, ends upon a dirty part of the carpet and vacuums it successfully, I suppose just the sheer amount of dust it sucks in could be a measure, could be used as a reward function. How much dust did the Roomba suck in at this particular action? Well, that could be a reward function. It's as simple as that. And so what would the Roomba do? It needs to navigate the room with all its furniture, trying to maximize the overall reward, right? Which would be gather as much dust as possible from the carpets, right? Whose effective result would be to vacuum all the vacuumable parts of the cleanable parts or accessible parts of the room. So that is one easy way to think of reward in this case, is the dust that the Roomba gets. Now let's think of the same thing in the context of an LLM. If an LLM is an agent and it has gotten a prompt, let's say that it has gotten a prompt. A prompt is a text, and because it's a text, what is the initial state of the world? The S0 state is the prompt itself, isn't it? The query. All that we know in the environment is there's the question hanging in there. And then the LLM produces, acts. What is the action that it will have? It will produce a token T0. This is your action. T0 would be the action. And when you do that, what does S1 become? The state of the environment become? It becomes prompt, comma, T0. Right? You have a new token generated. And so the LLM can observe that. And in fact, that is literally what happened because of the autoregressive nature of the LLM. The T0 gets given back to it along with the prompt. And now it has to produce the next token. And so the next state would be prompt 10, T0, T1, right? And so it continues. So our state K would be equal to the prompt and T0, T1, all the way to Tk minus 1, Tk minus 1, right? Something like that. So at each step, the action that the LLM takes is to produce a token. Action, therefore, in the language of reinforcement learning, action here is simply the LLM producing a token. Now what happens is that at any given point, let's say that you are in the state Sk. Is that a good state? How good that state is? How likely is it to solve your problem? Let us say that the problem is that, let's take a problem. Mary had 20 apples, and this will contextualize the rest of the paper. She gave 6 to her neighbor, 8, 3, and 1 went bad. How many good apples does Mary have left? Suppose this is your prompt. You can clearly see that this is a reasoning prompt. It expects a certain degree of reasoning. And so let's say that your machine starts producing tokens. And the first token that it produces is, let's say that future, it says Abra, Kadabra, Hach, Poch, something like that, 4 tokens. So this is scenario 1, number 1. Number 2 is, since Mary had 20 apples and she gave away 6, and therefore, and let's just stop here. Because this is an intermediate state. I'm just looking at some intermediate state Sk. And let's look at the third thing, intermediate state, in which it basically says, clearly, Mary has 10 apples left. Now, let us say that the machine is continually producing tokens. And consider that this is, you don't know whether it is done producing more tokens, right? Whether this whole trajectory of actions is over. Okay? A trajectory would be pretty much the answer, the tokens, the sequence of tokens that the LLM produces. You would agree that we can associate a goodness measure to every state. S1, a goodness measure S2, and goodness measure S3. Intuitively, we would say that it is far better to be in V2 than in V1, the state S2 than in S1. Because from S2, it seems that you're heading towards the answer. S1 seems rather hopeless, isn't it? And so as the machine produces actions or tokens, at any given moment, you can sort of critique the output so far and attach a value function to it, a goodness measure of that state. How likely is it that from that state, you can go to a good answer? Okay? Now, this is usually captured in terms of a a little bit more mathematics that we'll cover in this, but that is a very important thing. That's value function. We just introduced the concept of a value function. Value function is associated with a state. It's a state-related value function. Now, let us say that the machine is thinking, and at that moment it is undergoing training, and you are doing some loss and you're back propagating the loss and so forth. So at the end of it, the machine is trying to guess, am I in a good state or not? Right? What is a good state to produce? And not only that, let us say that there is a reward function. For every action, you're somehow able to reward it. Now, you may not be able to give it a reward at each token. You might give it a reward if it comes to the right answer at the very, very end. So therefore, there are two kinds of reward processes or ways to do it. One is if you keep getting rewards step by step by step, you have a process optimization. The machine can learn to policy, can create a policy, process policy optimization. It can basically say, hey, all I need to do is figure out how to get the next big reward. Or if you can't, if it is just outcome based, so the machine, the LLM keeps producing tokens and it reaches the end. And at the end of it, you like the answer. Yeah, it says that Mary has 10 apples left, no matter how you reached. And then you get a positive reward, otherwise you get a zero reward. So then you do have a problem. The problem with outcome based rewards is that how do you have an attribution problem. How do you know which steps in the journey, which of the actions were better actions and which were misleading actions, or which were detrimental actions? Why did you succeed and which step needs to be rewarded more? And how do you ascribe credit to each of the steps or actions? That becomes a problem with that. But nevertheless, you have an action, a value function. You also have, for every action, you would agree that given an action AI, or given a state SI, you can associate a quality of the action, how good that action is. Right? So for example, if you're playing tic-tac-toe, let's say that you have something like this, and 0, and you have to put a cross, you would agree that an action that puts a cross here is better than an action that puts a cross or a cross here. These two are better than putting a cross, let's say, here or here in the two dotted places. Oh, actually, even that would be great. This is too easy a problem. I made it too easy. Okay, well, yeah. So let's look at this. You're in this state. You would agree that the only good cross that you can put to win would be here, right, at this particular moment. And so this is a better. So you have something called quality of action. And quality of action usually is a measure of how good it is. And what happens is you can take many actions. For example, you can take, let me call this A, B, C, D. These are, you could have put a cross in any one of those 4 locations, and each of them is a certain quality of the action, how good that action is. Each action has an advantage, right? Advantage is a measure of how likely is it to take you towards a win, right? And so that is called the advantage function. Advantage, AI, is whatever action that you take, how advantageous it is, right? Compared to the quality of action, QI, minus an average action, minus an average quality from the previous state. Like, see that you're in this state. You could have taken A, B, C, D actions. What is the average reward you would get, or the value there is in B? That is measured by the value of the state. So it's a little bit of a technical stuff. Value of the state is a measure of, in average, how much reward can you get, right? And therefore, the advantage of an action is how much it will, it deviates from the average, right? And that's sort of the word that people use. So with that kind of a background, what you have is the machine has something called a policy. Policy is nothing but the parameters of the model. You give the policy of a LLM as pi theta, which basically means, what does a neural network do? It comes up with the next token. It's a policy of generating the next action. In the case of LLM, it's very directly its propensity to produce the next token, which completely depends upon the parameters of the model. So in some sense, you can say that the model itself is the policy, right? In the case of LLM. Right? So you can do at every step, as the machine learns, it tries to come up with a better and better policy. Policy would be producing a better token, right? A better policy is something that produces a better token that takes you towards the answer. Now, what does a policy look like in the case of an LLM? So imagine a language which is made up of just 5 words. Let's say we have the word A1, A2, A3, A4, A5. Or you can go on to A. Okay, it doesn't matter. This is your vocabulary. Now, you would agree that this LLMs, they have a certain probability distribution. Given a state Si, it has a certain probability distribution of what the next likely word, what should be the next word, next token. And in effect, that is the policy. Right? What you would do is you would sample off the policy, y, the next token, t, would be sample of this policy theta and produced. And then you would have a loss, and then the usual things come about. Right? So in the case of an LLM, the policy quite literally is the probability distribution over the token, over the vocabulary. Right? So this is, I don't know, it might be too fast or too slow based on where you are in your understanding of reinforcement learning. But see, policy is, so the LLM is the actor because its job is to produce the next token, right? And it does it with its policy. And its mathematical representation is its policy or just the parameters of the model. There is a critique here, and the critique is the value function. Given a state on which the actor will act, that state, how good a state it is, right? How good the state it is that you produce, that the actor has produced. So actor acts, and the critique, essentially the value function, gives you a measure of how good a state you ended up in. So that's why these models are often called actor critique models. Right? And of course, implicit to all of this is a reward function. Now, one of the interesting contributions of DeepSeek was that it actually took away the critique and replaced it with something different. It simplified the whole story quite a bit. And we're going to cover that in this paper. So now, with that as a background, let's try to read this paper quickly and see how much progress we can make. Otherwise, we will cover it. We'll sort of finish it the next time. But let's go to the high-level ideas of this paper. It says, large language models, LLMs, have transformed the natural language processing landscape and brought to life diverse applications. Pre-training on vast web-scale data has laid the foundation for these models, yet research community is now increasingly shifting focus towards post-training techniques to achieve further breakthrough. Once again, by post-training, you have to take the word in context because it doesn't mean purely at inference time. Post-training means after the pre-training is done, everything that you do after you have landed up with a pre-trained monster. Yeah. So while pre-training provides a broad linguistic foundation, so what does pre-training do? The machine learns to understand human language. Post-training methods enable LLM to refine their knowledge, improve reasoning, enhance factual accuracy, and align more effectively with user intent and ethical considerations. Fine-tuning, reinforcement learning, and test time scaling have emerged as critical strategies for optimizing LLM performance, ensuring robustness, and improving adaptability across various real-world tasks. This survey provides a systematic exploration of post-training methodologies, analyzing their role in refining LLM beyond pre-training, addressing key challenges such as catastrophic forgetting. So what is catastrophic forgetting? Catastrophic forgetting is a very peculiar problem you have in models. See, you have trained the model on pre-trained data, the web scrape data. Now you bring in a supervised fine-tuning data whose probability distribution is vastly different from the nature of the original scrape data, web data. What it will do is, in a very intuitive sense, the model will say, aha, maybe all that I knew was wrong. I need to, because now I'm seeing a different reality. And so it will actively forget. It will go through a process of forgetting what it knew, and it will just align to the new reality. Whenever you do supervised fine-tuning or you do fine-tuning, there is always a risk of catastrophic forgetting. It's a fact. And within those lens, you can almost say that everything that happens after the pre-training, to different degrees, has that risk associated with it. Reward hacking. What is reward hacking? Reward hacking is, you realize that the LLM is a policy, in some sense, a policy model. What is its goal? It knows that if it takes an action, it will be given a reward. There is a reward model. Usually a reward model is a reward neural network in itself. So what it will do is it will try to game the reward model. It will look for weaknesses in the reward model, right? And when it does it, it will exploit those weaknesses. So instead of learning from the reward model, the lesson that it had to learn, it instead learns to hack the reward. So that is called reward hacking. So one example is, let us say that for some reason, the machine is solving multiple choice questions. And it just happens to notice that the reward model just a little bit gives preference to answers. Correct answers often tend to be from A, B, C, D, they often tend to be C. So what will it do? It will just try to give lots of C's as answer. Like in the unless it has a reason to, it will gravitate towards C. That's an example of reward hacking. And so it's very hard to reduce subtle weaknesses in the reward model. And reward hacking has been a problem for quite some time. Actually, with PPO, it was a considerable problem. And inference time trade-off. Another thing is inference time. How much time do you give to inference? The more you let the machine reason, the longer it takes to answer your question. Most of you have noticed that if you use a reasoning model, you better not ask it, what's the capital of United States? It might go into a deep philosophical reasoning process or something like that. I'm joking, of course, but it does take a lot longer. It begins to reason what could be the capital of the United States. Right? It is not, well, that is a caricature. I'm sure it will do that problem very easily, but you don't want to ask it problems for which there is straightforward answers in memory indirectly. So even if it knows, it will say, I happen to know that this is the answer, but since this question is asked, maybe I need to think through and be careful. Right? So that's inference time trade-off. Whereas if you ask a non-reasoning model, a more traditional model, what's a simple question, if it knows the answer, it will immediately spit out the answer. So that is, and then of course there are hybrid models. Now, for example, just this week came out Qwen. Qwen 3 has the ability that you can switch from reasoning to non-reasoning modes. It is purely, essentially a flag. You can go from this mode to that mode in the same model, right? And you can even do it at a per query level. In the query, you can indicate use reasoning or don't use reasoning. Right. So we are, of course, in a completely new world now. For the last 2-3 months, it's surprising how much the world has completely changed in the last 2-3 months. So this paper, I won't go through all of the things, but a few things are worth mentioning. Despite these impressive achievements, LLMs remain prone to critical shortcomings. They can generate misleading. They can generate misleading or incorrect answers, hallucination. And may struggle to maintain logical consistency through extended discourse. So suppose you have a long reasoning session with it, sometimes it loses its own train of thought, right? And you see that. Nevertheless, we all agree, especially in the engineering community, we all know the priceless value of these AI models. In fact, most of us now use IDEs that are AI assisted. Right? We write code with the assistance of AI. It doesn't mean that we let it write everything. The vibe coding extent in which somebody says, I don't know programming and I don't need to know programming. I can just sit before the machine and talk to it and it will write the code for me. So there is a no code vibe programming revolution in progress. But most of us engineers don't go to that extent. What we do, I suppose, is AI assisted. More like we write something, we put our thoughts, we put our outlines, we write a function definition. We let it complete, then we go give it feedback that this is not correct, change it this way and that way. And that is how we spend most of our day. So the value of reasoning models is pretty self-evident. In fact, this year will be the year where the greatest evolution will be in reasoning models. Therefore, the value of this survey paper. While these models can produce responses that appear logically coherent, their reasoning is functionally distinct from human-like logic inference, which is true. Actually, one of the remarkable things that I find with reasoning models is, suppose I've thought through an issue, especially in code. I would write some code and I would think that I have covered the bases, all the bases. And I usually ask it to look very carefully at all the possible corner cases and critique it. And we pleasantly surprised how often it immediately catches things that I didn't think of. And I started coding way back in 1985. So after all these years, I still miss some cases or some aspect. And it's amazing that the reasoning models of today are so capable of spotting it. and immediately bringing it to my attention. The past used to be that I would write something and I would go out for a walk and then remember, oh, I forgot that, I forgot that. What about this? And then come back and do it. And it would be an iterative process. And I would never be sure in a very complex system that I'd covered all the bases. Right? You never do. You can write only so many unit test cases and still something leaks through, remains, and there are situations or scenarios that remain unthought of. So I find that reasoning models are certainly invaluable these days. Right? But what is also interesting is how often they are wrong. Like I can't even, maybe it's just today, the complex codes that we write, I notice that it almost never gets it right the first time. It will produce something, you go review it, and then you say, no, 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 not like this. Oh, but by the way, that is wrong. And you ask it to just write a test, and it will say, oops, yes, I got it wrong. So it seems to be, at the same time, extraordinarily clumsy and yet super intelligent. It's quite interesting. In areas, it thinks very, very deeply and reasons very well. And yet, when you engage with it very closely, it sort of blunders forward, right? It moves forward clumsily and it keeps making mistakes that you keep pointing out. And then it fixes it. And that's how you make progress when you're writing complex code. Or at least that is my experience. I would like to know what experiences you people have. Okay? So now it talks about, so I'll just jump ahead and say, what is reasoning? This paper defines, for the scope of this work, reasoning in LLM refers to the ability to generate logically coherent responses based on statistical patterns in the data, rather than explicit logical inference or symbolic manipulation. Right? Well, we'll just stick to the intuitive definition of it. Adapting LLMs to domain-specific tasks often involves fine-tuning, etc., to add, which enables task-specific learning, but risks overfitting. This is a point that we made, and incurs high computation costs. Remember, the two problems that we said is supervised. The fine-tuning data is supervised training data is always very expensive to create label data. Right? And the second thing is it will invariably sort of your machine will try to overfit to it. Right? And those risks remain. So to address these challenges, reinforcement learning enhances adaptability by leveraging dynamic feedback and optimizing sequential decision making. Actually, this is a lot of big words, but basically what it says is that if you have a process reward model, in other words, it produces a token, it does, and you tell it how well you're doing. In some sense, supervised, like when you do pre-training is somewhat like that. You ask it to predict the next token and you compare it to the next token you had. But in reinforcement learning, you have the option that you just wait a little bit and you let a few tokens come out, or let all the tokens come out, and based on the outcome, then you give a reward. So you force it to move away from just being able to see one step forward and optimize only that, but to optimize, produce a whole sequence of tokens and optimize across that, because the reward function is across a whole bunch of tokens. That was one of the lovely results that came out with reinforcement learning. So that is what we are meaning, optimizing sequential decision. So additionally, advances in scaling techniques such as low rank adapters. So now we are talking about test and scaling. Like for example, you have LoRa to fine tune retrieval augmented generation, etc., etc. So let's leave that aside. Now we go to fine tuning. And I'll just read the boxes because very helpfully this paper mentions these boxes. Fine-tuning tailors LLMs for specific tasks, improving performance, but risking overfitting, high compute cost, and reduced generalization. Well, overfitting and reduced generalization are literally mathematically synonyms. Now, reinforcement learning, on the other hand, with the introduction that I gave you, I'll just read the box. Reinforcement in LLMs extends beyond conventional reinforcement learning as it navigates vast action spaces, handling subjective and delayed rewards, and balances multiple objectives, necessitating specialized optimization techniques. Quite a mouthful of a sentence. Let me unpack it. See, when you play the game of tic-tac-toe, right, the number of states possible are finite, isn't it? It's a grid with ultimately just 9 places, and there's a finite set of states that you can be in. Right? On the other hand, imagine that you have a vocabulary. I'll just take an example. Suppose you have a vocabulary in English which starts from the word aardvark. in the dictionary. And what is the last word? Let me just call it that word is the last word in the dictionary. And this dictionary is, let's say, 30K words or 1 million words. These days, 5 million or bigger numbers are common. I'll just round it off to a million. So what does it do? At any given moment, what is your action? Action of an LLM is, in the reinforcement learning scenario, is what? To produce the next token. Now, how many tokens are possible? The vocabulary is 1 million words, 1 million tokens. Therefore, you have to choose between 1 million possible actions. You realize that. So you produce a token, 1 million choices. You produce the next action, action A1, action A1, action A2. Again, you have a million choice. You realize that the state space that you're looking at is nearly infinite. You don't know what will be the final length of your answer. And at each point, you have 10 to the 6 choices. So suppose you produce 100 tokens as your answer. You realize that you're looking at 10 to the power 600 as your state space. Now, that sort of state space is very, very hard to associate value functions, to bring the traditional architecture of reinforcement learning. Think tic-tac-toe, right? Or a Roomba cleaning a room. It's very hard to take what works for finite tractable state spaces to this linguistic domain, natural language domain, where the state space is so bizarrely huge. So that is the challenge that these authors are speaking to, and they are saying that makes the use of reinforcement learning within for LLMs particularly hard. So let's reread this sentence. Reinforcement in LLMs extends beyond conventional LLM as it navigates vast action spaces. So why is it a vast action space? 1 million possibilities. Right? Handles subjective and delayed rewards. You might be told the answer, whether it's correct or not, after you have produced the whole answer. Or there's subjectivity, because those answers, if you're bringing in human feedback, reinforcement learning with human feedback, what do? You produce many, many outputs, give it to human beings to stack rank it. So there's subjectivity that comes in, there's delayed rewards here, and balances multiple objectives, right, that are there. When you're doing it, there's human alignment, there's correctness of answer, and so on and so forth. Right? All of these things have to take place when you do reinforcement learning for LLMs. Now, test time scaling in LLMs. Of course, here we are referring to things like LoRa, RAG, and many things, chain of thought, etc., tree of thought, etc. So this you guys are all familiar with, so I'll skip through this. So test time scaling enhances the adaptability of LLMs by dynamically adjusting computational resources during inference. Right? So that is that. Now, their prior work I'll skip. What is the main contribution of this survey? And I suppose we're running out of time today. So why don't we take it up perhaps next time to continue with it? I apologize that the setting up the introduction took me so long. The key contributions of this survey are the following. We provide a comprehensive and systematic review of post-training methods for LLM, covering fine-tuning, RL, and scaling as integral components of model optimization. We offer a structured taxonomy of post-training techniques, clarifying their roles and interconnections and present insights into, etc. Our survey provides a practical guide by introducing key benchmarks, etc. So guys, this paper covers some key ideas. I'll just jump through and give what we have. It covers a lot of territory. It's almost, when it comes to reinforcement learning, it pretty much condenses a textbook of reinforcement learning into a few pages, right? You see pretty much the history of reinforcement learning, especially in the context of LLM, reproduced here, right? You see, for example, the value function, the way that I explained, action, the quality of the action, the advantage function. Now, these things are not things that you can just sort of immediately understand by reading the paper. You do need a background in reinforcement learning, which is why I was trying to give a few motivating examples to do that. And so the earliest policy gradient, like how do? You know that you can do gradient descent. We learn in machine learning through gradient descent. The whole thing is gradient descent of what? And so here's the intuition that I want to give to the most important thing called the policy gradient. I would like to end with that. See, all policy gradient things are like this. Suppose you are in a state space, right? So suppose you have two parameters in your model. Suppose a neural network has just two parameters, theta1 and theta2, right? And this is the theta1 direction, theta2 direction. Now you know that every single point in this space is a policy, isn't it? Pi theta. Like every point is basically some combination of theta1, theta2. It represents some state of the model, and therefore it represents a policy. Now, that policy could be good or bad. Maybe the best policy is here, and nearby policies are just as good. And just for the sake of argument, I would assume that it is a bell curve, a bell hill, right, in theta1, theta2 space. So what can you do? Let us say that you start, this is your standard gradient. You start here. Suppose you start here, start. What do you need to do? You need to go up the hill to reach this point. You want to reach, and by the way, what is the y-axis? How good the policy is, right? The optimality of the policy, how good that policy is in extracting rewards, right? So you need to start from some policy and make it a better and better and better policy. Does that make sense? So you have to do hill climbing. How do you do hill climbing? You take any value of theta, and then you say that the next value of theta is that theta plus the gradient of the policy theta, right? You take the, because this is the policy function, right? You take the policy, the gradient, it will take you, remember that a gradient descent would have a minus sign, gradient ascent, hill climbing would have a positive sign. This is your basic math. So it would take you up the hill, right? It's a hill climbing approach. And in some sense, let me see if they mention it somewhere, because this all reinforcement learning basically starts with that equation. Oh, here it is. And what you do is you always do the log of policy for reasons that, for example, you notice that policy is a probability, you remember, negative log likelihood and so on and so forth. So for the same reason, and for computational stability, you always do log of the policy itself. But gradient makes total sense, I hope, right? And that is the main message. If you look at the equation, and I want to do that just to give you the key intuition of how these things work. Look at this equation. I hope this equation now makes sense. Look at this. We are looking at the gradient of the policy, well, the log of the policy, and we are saying that the new policy, the new value is the previous value plus alpha, the learning rate, which you would always have, times, I forget the g minus b part for a moment, times the gradient, right? So you're trying to move up the thing. Now here, so there's something called the total reward accumulated over the entire episode. Like if you continue this journey, how much reward you get, and B is a baseline reward. So there is a little multiplying factor here, G minus B. But just to understand or get the basic idea of a policy gradient method, which is the earliest method, just ignore the G minus B for the time being. And then the rest of the equation will look to you like your standard hill climbing equation. I hope. Hill climbing. You want to go to the best possible policy, train the parameters towards the optimal policy so that it extracts the maximum reward. So this paper doesn't talk about this hill climbing intuition, but in my mind, I've always carried this intuition. Now, there is another method. So this is the old history of it. People realized this a long time ago. Right? This is the famous policy gradient or the reinforced method of reinforcement learning. Then came another method, which is called curriculum learning, which basically says that, hey, let's do two things. Let's use the traditional maximum likelihood estimation and reinforcement learning. A little bit. So whenever you see lambda and 1 minus lambda, it basically means lambda will take on values between 0 and 1. So let's say 30% of this and 70% of that. Right? That's what it means. So a little bit of reinforcement learning and a little bit of supervised, the maximum likelihood argument, MLE argument, right? You throw it into the mix. And so there are many other methods, but at the end of it, we come to the advantage actor. Remember the advantage function that I said? What you do is you replace this thing with what is called the advantage function that we just said. How advantageous is this action compared to other actions from this state? Yeah, that becomes your multiplying factor. So this is where we are today, right? And this again is the actor critique model. One of the big breakthroughs recently has been that we have departed from the actor critique model. especially in GRPO. We don't do that. Yeah. And we'll go over these details. I suppose this paper is actually quite nuanced and quite technical, and it needs a lot of reinforcement learning background to make sense of. I will be, though, happy to cover this paper carefully, one by one, equation by equation, but it's a little bit longer journey than to cover it. So I would like to stop here and take some feedback. I don't know if everything that I said, any of it was proved useful or not, because I realized too late, actually today, people had asked me to explain this paper. And as I was talking about it, people then prefaced it by saying, oh, by the way, could you also give us some background? It is too full of equations. Background and reinforcement learning. Reinforcement learning is a whole subject. And I tried to give a little bit of a background here. Anyway, guys, I would like some feedback. Was this useful at all? Because I just realized too late that this is one of those dense papers that needs a lot of background to be understood. And nevertheless, it is a pivotal, today reasoning models are the big thing happening all around us. It is the area of greatest research. It is interesting that we are talking about reasoning model today because imminently, any moment or any day now, R2 is about to come out, DeepSeek R2. There are already rumors flying around that it will be another significant advancement. Frankie, you have raised your hand. Please go ahead.
Yeah, got a little bit confused. I'm not sure if it's okay to talk about it now, but I thought that you want to you're trying to maximize the return, right? So it feels like you should always be taking the gradient of the return as to be the steps towards your updating your parameters. And I think the fact that you're updating the log of the policy, it's actually a simplified version of the gradient of the return because it doesn't take the advantage into consideration. So, but typically, you're trying to do the update on the gradient of the return.
No, yes, you're very right. So let me just explain it a little bit differently. But your intuition is absolutely right. See, here's the thing. Suppose this is the you are at this location, right? You're at the start location. The problem is you don't know the reward, right? Reward is something that will come. I'll give you an example that will give you a sense of it. Your Roomba moves forward. It realizes it gathered some dust, right? But it moves sideways and at an angle it realizes it gathers a little less dust. Right. So your basic intuition is that, hey, so I should have been moving forward rather than diagonally because, the reward was the amount of dust I could gather. Trouble is, reward comes after you act, right? And the policy is its hypothesis about the reward system. The neural network, the LLM is in effect, or any neural network, the agent is trying to figure out exactly what is the shape of the reward function. And what it is therefore doing is it is searching in different directions. Which direction should I go to maximize my reward? And what happens is that you change your policy a little bit, just a little bit, and that will lead to a certain advantage. And so that is why implicit, remember there was an advantage function that is implicit here. That advantage function is literally the container of the intuition that you said, that you need to move in the direction that increases your reward, maximizes your reward. You need to have your gradient pointing in that direction.
That's correct. So you need to have the advantage somewhere. Otherwise, just taking the gradient of the log of the policy doesn't quite make sense to me because you don't know where you're supposed to go by just looking at the log of the policy.
Definitely. No, here you're absolutely right. Actually, I oversimplified it because I wanted to make it look just give the intuition of hill climbing, but it is hill climbing within the context of an advantage that takes you there. That advantageous action that takes you there.
Asif, this is Shankar. One quick question. You mentioned that you have 10 to the power 600 possible next states because the LLM has such a big action space. Given that there are so many different next states, how it must take a horrendously long time to assign a reward for every possible state.
Yeah, that's what makes reinforcement learning so hard and so fun. Think about it this way. What are the applications of traditional reinforcement learning? Beat you at the game of chess, at the game of Go. Can you imagine what is the state space combinatorially of a chess game? Impossibly, like there are more possible moves in chess, of games in chess, than there are atoms in the universe. by a huge amount, by a huge factor. So that is where reinforcement learning actually shines. At the end of the day, to deal with very, very complicated problems, sometimes you have nothing left but reinforcement learning. That is what you have to use. That's why it's such a fascinating and powerful technique, though computationally brutal. And like, obviously, see, today I'm trying to give you guys a very, very intuitive sense of what RL is, because this reasoning models and RL have become practically synonymous today, especially since DeepSeek. So, but it's a big field. I mean, this paper, I can't believe it. Like when I look at it, we are looking at starting, this paper starts with quite literally the earliest methods. For example, pairwise preference probability, and even before that, it starts with TRPO. TRPO was used with some early robotics, right? And and many things have to explain. What is the KL divergence here? It basically says that you can change your policy, but don't hop around the policy space. Change a little bit, stay within a circle of change. Otherwise, there'll be a penalty. There's the KL divergence factor. And PPO is basically saying, again, clipping it a little bit. And GRPO is, these are special policy optimizations. But I would rather not just rush through it in one-liners, because I don't think that will help anyone. If you want, I can give you some flavor of it. But perhaps, or maybe let's keep it for a proper analysis next time. One thing that I would say, though, see, reinforcement learning has always been considered a bit of an academic part of machine learning, and not as overwhelmingly used in the industry, which has mostly done classification, regression, clustering, dimensionality reduction, and recommender systems and things like that. But now, reinforcement learning is becoming front and central. We are just realizing the enormous power of reinforcement learning, especially in the context of LLM. If you read the paper DeepSeek, and I highly encourage you to do that, you will see the sense of amazement and euphoria the researchers felt when they saw that just purely through reinforcement and nothing else, the model is able to reason. And they said that we had really underestimated the power of reinforcement learning. Right? And just pure reinforcement learning. So reinforcement learning is a big thing. I would highly encourage you to take one of the two textbooks on RL. One is, of course, the Sutton's great classic, Sutton being one of the Turing Award winners, of course, the Sutton of the same greatness. He has written the definitive textbook on reinforcement learning. It's a little dated. Most of these policies that we are talking about in this paper, that book predates this. I think that book is in need of an update. Nevertheless, it's a great book. And the other book, that a little bit more accessible book and a quicker, easier to digest book, I just brought it off from my shelf. Thought I'll show it to people if anybody is interested. It is called Grokking Deep Reinforcement Learning. I'll just put the name of the textbook here, so that, because I noticed that a lot of people find it really useful. Grokking Deep Reinforcement. It's a very good book. I would say that it's a very good book, and one of the quickest ways that you can ramp up on reinforcement learning. There are also excellent YouTube videos. I'm surprised how suddenly there has been a pretty rich harvest of very, very good videos on reinforcement learning. And when I look at this paper, I'm realizing that reinforcement learning applied to LLMs, this paper is essentially, to a large extent, a summary of that. It has other pieces also, but that is the core of this paper, the survey paper. Right? The rest of the things most of you are already familiar with, like beam search, trees of thought, chain of thought, and all of these, prompting, compute optimal scaling, and so on and so forth. We are familiar with this, but the new thing that comes out in this paper is it has summarized everything, the reinforcement learning applied to LLM very well in one place. But to the extent that it's a summary and a survey, it takes quite a bit of effort to make your way through it if you don't know RL. Any questions, guys? If not, then we'll end today's session. Thank you for being a part of the Support Vectors learning community, guys.